Okay, get your answers in.
This is from the sweat's perspective. This is relative to the sweat.
This is the
Relative
reaction.
to the skin.
This is sweat evaporating, that reaction. Okay, I'm going to end it. Okay, wrapping this one up. Here goes. Sweat evaporating is definitely endothermic. Okay, next question. The last reading quiz question is, will this reaction occur spontaneously as it's written? You're given the balanced chemical reaction, and you're given the delta G for that reaction. Can I zoom in? Sure. Okay, we're going to end this one. Answers in, A or B. Wrapping up. Okay. Will this occur? The delta G is less than 0, therefore it's negative, so yes, it proceeds, right? So if you're having any questions at all on these ones were things that definitely you should have gotten from class. Because there's not a good reading in the book on thermo, these came from the previous lectures. In general, these will be coming from future things that you'll be expected to read. Our TA, Danny, will be posting those between Friday night and Saturday night for the coming week, right? So for the week that's coming up, watch for her to post what things you should read. And these are not meant to be difficult at all. These are just meant to be encouragement to read the chapter. If you've read the chapter, these should be really easy. Lonnie, question?
Yeah, do you post the questions after class? Or?
No, but I will record the lectures and you can always catch them. They'll always be the first 5 minutes of class, so you can see them that way. And I've assigned it, and hopefully it'll do it on all of them. You see the little green check here? That should indicate what the right answer was. Oftentimes it'll be what most people select, not always. Yeah,
Have you
Nick?
posted the previous lectures yet?
The videos? Yeah, all of those are available. If you haven't seen it, I made an announcement. There's a YouTube playlist, so it'll just automatically play all the lectures. I've got the first, I think, 4 days of class plus 2 bonus lectures where I talk to the MSc 2010 students about how to write nice lab reports. That's all available. And let me actually pull it up to show that we've gone through some work on this. So if you go to the course website, there's a link. Otherwise, let me just pull it up real quick. So on the course website, there's this Excel spreadsheet where I've got the date of class, I have the chapter material that we covered, and then I have a really well broken down list of the topics covered and a link to the YouTube video, right? So if you go to this thing, grab this whole video, right? Come over here to the YouTube machine. It's actually hyperlinked, so if you don't want to watch the whole hour-long video, for example, blah, 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 right? You can scroll down here and click the exact section to go to what was covered, right? And we've actually done more detail in this. We have it broken down almost every 5 minutes, so we're trying to make it as easy as possible for you to review stuff that was covered in class, and this is the easiest way I know how to do it. If you have suggestions, I'd love to hear them, but why don't you send me an email or come by my office to do so. Okay, let's move on then. Today, I finished up this activity of predicting whether or not a reaction will go forward. We did the first 2 in class last time, so I went ahead and I finished it. And the key point is that when both enthalpy and entropy both predict that a reaction goes forward or backwards, it's really easy to predict, right? If enthalpy is negative and entropy is positive, it's definitely going to happen. If enthalpy is positive and entropy is negative, it's definitely not going to happen. But then when you have competing results, it depends. The answer is, well, it depends. And oftentimes it's temperature, right? Consider this one. Enthalpy, change in enthalpy is positive. That's bad, right? That's endothermic. It's absorbing energy, right? However, the entropy is increasing. So here's one that's competing. Which one's going to drive it? The answer is, it depends. So you've got a positive term minus a positive number. Temperature is always going to be positive. multiplied by a positive number. So this is going to be positive minus a positive number. So if temperature is large, then that will actually cross over and become negative. If it becomes negative, it becomes spontaneous. Free energy goes down, right? So in that case, that type of reaction goes forward at high temperatures, but not at low temperatures. And then the reverse, let's say something that's exothermic, but it becomes more ordered. That's something that will become favorable at low temperatures, but not high temperatures. You'll see an example of that on the homework 2, which will be posted tonight. Okay? Yeah, question?
What does spontaneous mean?
Spontaneous means it will happen automatically, that you don't have to drive it. Today, we're going to talk about electrochemistry, where you can drive a reaction forward. That's not happening automatically. When we say drive, that can be electrically. You hook up, leads to it, and put a battery to it, and make it happen. But spontaneous means it happens on its own. That there's an energetic argument for it wants to happen. An example of this is, diamond, right? Your diamond ring, from an energy standpoint, the diamond in your diamond ring wants to turn into carbon. Do you know that? Diamond, if you put it in a fire, it'll actually, I don't know how hot it has to be, but it would actually eventually get enough energy that it would burn and turn into carbon, right? If there's oxygen present, it'll just burn, right? But if there's no oxygen present, it'll convert to graphite, right? That's because from an energy standpoint, it steps down in energy, so it wants to happen. That doesn't mean it's going to happen, though, right? Later this semester, we've covered thermo so far. Later this semester, we're going to cover kinetics. Kinetics dictate the rate at which things happen. Sometimes kinetics means it never happens, right? Like your diamond on your ring turning into graphite. Kinetically, that is an extremely, impossible process, right? So it doesn't happen unless you heat it up, like throwing it in a fire or something. Yeah, other questions?
If it's already happening, is it spontaneous? Or does it have to have started spontaneous?
There's more I can say about this. Let me introduce the idea of equilibrium, and maybe that will explain your answer to this, because if it's happening, then it was spontaneous. But will it keep on happening just all the way, or will it stop at some point? That has to do with equilibrium, and let's talk about that right now. Okay, if you guys remember 2 class periods ago, we talked about tabulating the change in entropy or the change in enthalpy for a reaction if you know what the individual components were, right? You did the sum of the products minus the sum of the reactants, and it wasn't so bad. Well, you can do the same thing with delta G, and we're going to do that for our next clicker question. The clicker question, that's big, make that smaller, is as follows. Here's your equation. You've got NaHCO3, that's a solid, turning into NaOH, which will be a solid, plus CO2 gas, right? So it's decomposing to form CO2 gas. So what I want you to do is calculate the delta G naught R, right? So delta G R, that means the change in free energy for the reaction, and then naught means under standard conditions, meaning that you're using these free energies of formation, delta G naught F. Okay, you're going to assign that, you're going to do products minus reactants just like before. Here's your 3 values for the 3 things in the equation, CO2, NaOH, and NaHCO3. So go ahead and plug this in and figure out whether the answer is A or B. Is it a positive free energy change or a negative free energy change? We'll do 2 minutes on this. Yeah, questions? So in the same order they appear in the equation, right? The last one is CO2, second one is NaOH, first one is the sodium carbonate. If you have questions, raise your hands. We have TAs. I can help too. If you're stuck. Okay, 20-ish seconds left. I think we're doing it right after the section. Will the thing on equilibrium? Maybe one more question. Should be good to go.
So you said the slide is
Thank you.
yellow.
That's the yellow.
Line up with that.
Will you get the so I know which end is which?
The short end.
Short end per volume. Okay, we're gonna stop this one. So answers in A or B. Maybe you can always ask a friend if you're panicking or if your calculator died. Rose, I'm gonna end this, then we'll answer your question. Okay, people think A or B. People think. I don't know why this is so slow. Most people think positive. Is it positive or negative? What did I get? Oh, it is positive. It's positive. Now, how do we do this? Let's just write it out really quickly. Delta G, again, the change in the free energy. So delta means change, G is our energy, R means for the reaction, and then 0, the little 0 up here means under standard conditions, right? Meaning that we use these delta G naught of formation values. Again, we do products minus the sum of the products minus the sum of the reactants, coming out to 77.2 kilojoules per mole. Okay? Now, because that's positive, leads to our next question. It is a positive delta G, so is this spontaneous or not? So answers in, answers in. Just do 1 minute on this. Okay, anybody need more time? I'm gonna go ahead and end this one. Okay, and because it is a positive change in free energy, that means it went up in energy as this expression is written. Therefore, that will not be spontaneous. What does it actually mean then? That it'll go the other way. That if you have NaOH and CO2, and you put those in a beaker, at least from a thermodynamic standpoint, ignoring kinetics for a moment, those things should react to form this NaHCO3, right? Spontaneously. Okay? Any questions on this? That straightforward? Yeah, Rosa.
So I don't understand why. I thought last time, or even lecture, we were saying that don't count solids.
Great question. So where did solids and liquids versus gases come in? That was when we were talking about the reaction quotient. So the reaction quotient is this Q. We're going to come back to that just right now. And that's where you do the products over reactants. And if it's a gas, then you use the partial pressure of that gas. And if it's a solid or a liquid, they just put 1, meaning you can just leave it off, right? Now, what is Q? If you remember, our total change in free energy for reaction had 2 parts. And this is something I'm going to mention ad nauseum. You'll hear me say it so many times. The change in free energy can't just be calculated from the equation as it's written on paper, right? This one, as we saw it up here, that's how it's written on paper. And we all decided that on paper, when we calculated it from the delta G naught Fs, that's the free energies of formation, that's what the F is, under standard state conditions, that this looks like this won't happen, right? But that's the theoretical part of the equation, right? So in this equation here, that's this blue part, right? That's the theoretical part, delta RG naught. But it's not only a theoretical part, you have the experimental part, which basically is a measure of, well, what's inside the reaction chamber. If you have no CO2 to start, even though CO2 wants to combine with NaOH to form the other thing, it can't go forward, right? So there's this experimental and theoretical component that you have to consider, and that's where the solid liquid gas thing came in. So let's do an example of that. We'll do, I think, one more example here. Okay, how about this? Same expression. Again, we had the experimental portion, theoretical portion. Same time though. We're going to take the same reaction, the NaHCO3, reacting to form NaOH and CO2. This time we put it in a chamber that has, let's say, pure CO2 gas in the chamber, right? So you've got your lump of NaOH at the bottom, and the rest is CO2. So we know that this reaction, it should start reacting. Now the question is, the reaction will reach equilibrium when delta Rg equals 0. That's not delta Rg naught. That's, just to clarify, to draw a distinction here, we're talking about this one. When that delta RG, when the change in free energy for the reaction equals 0, it won't be going forward or backwards. Technically, it's going forward at the same rate that it's going backwards, right? There's no change in products. It's going to reach equilibrium. So the question is, when that occurs, what will be the final partial pressure of CO2? Let me help you get this one set up. We know that delta RG equals delta RG naught plus RT natural log of Q. R is the gas constant. That's 8.314 joules per mole Kelvin. Temperature needs to be in Kelvin. Just use, let me just write Kelvin. Put the temperature there in Kelvin, right? Q is our reaction quotient. Somebody remind me, how would we write the reaction quotient for this reaction? It's products over reactants. And in this case, we have two solids, right? The first solid reacts to form another solid plus a gas. So what do we have to write here? It can be the partial pressure of CO2. Then times 1 divided by 1, so you just leave those off basically, right? So Q just equals the partial pressure of CO2. Now initially, the partial pressure of CO2 is just 1, right? But we're not asking that. We're saying at equilibrium, what will the partial pressure of CO2 be? Some of that CO2 is going to get consumed to react with the NaOH to form the NaHCO3. And we want to find out what will be the gas pressure in this thing when it's done reacting, when it's reached its happy place and it's at 0. So all you have to do to solve this question is assign this left-hand side of the equation to be 0 equals delta RG naught, which we calculated previously. We said that it's a positive 77,200 joules per mole. That was what we calculated for our change in free energy. We're going to do plus 8.314 times, that's joules per mole Kelvin, multiplied by 298K, multiplied by natural log of Q. And you just have to solve for Q. So go ahead and do that. We'll take a couple minutes. That's our next clear question. Should we put it right after this?
That's okay. Should make them taller.
I'm going to move that kind of out of the way so you can see it. We're solving for the partial pressure. We know that Q in this case equals the partial pressure of CO2. That's not always the case. Sometimes it can be something else. In this equation, Q equals the partial pressure of CO2. Because our reaction quotient only has one term in it.
Probably still be the
Oh, yes, that's flickering.
That one's filtering. That one I think I need to add.
Okay, get your answers in. One more minute. Make sure you're using the temperature of room temperature, 298K. Okay, we're going to end this one. Get your final answers in. Phone a friend if you need to. Is that a good one? Okay, I'm wrapping it up. People think, what, is it A or B? Okay, it is A. That's right. Okay, so again, all you had to do was just bring one of these terms to the other side, divide it, take e to that side to get q on its own, and you'll find that q is equal to the 10 to the negative 14th number. Okay? If you're not getting the right answer on these, you can feel free to stop by one of the TAs. We can work through them in detail. Rosa, can I answer a question?
What are the units of Q?
Great question. What are the units of Q? So Q, we're going to use partial pressures for gases. And up here I wrote what that is. Partial pressure should be in bars, or ATM is fine in this class, so atmospheres. So if you have 1 atmosphere of CO2 in there, then you just put in just 1. So don't convert it to torrs or anything like that. We want atmospheres. Okay. Okay, so that's all the thermodynamic stuff that we're going to cover. Now we're going to switch gears and talk about electrochemistry. And at first these things might seem very, very different to one another, electrochemistry and corrosion and thermodynamics. They're actually remarkably similar. I'm going to show you what I mean. There's one correction. An equation in the book is wrong, so take note of that. That's equation 16.17. It should be this. I think they've got one of these subscripts wrong. I think that's one of the only corrections we have to do on the book the whole semester. Right? Okay, electrochemistry, that has to do with, just like thermodynamics, many of those reactions have to do with the oxidation and reduction, meaning that there's a species that loses an electron, one that picks one up. Electrochemistry has that happen as well. And this is basically what happens. You can take zinc and put it in a beaker with some zinc 2+ ions in solution. You can take a little reference electrode here, that's platinum, basically, that has hydrogen atoms here. Hydrogen ions, I should say, in solution. And if you connect this thing electrically, I mean you connect a wire to these two things, you will find the following. The metal, the zinc metal, actually gets dissolved, right? It starts to actually disappear. And you get hydrogen ions going from ions to bubbling into gas to form H2 gas. And you'll see gas coming out of this thing. Happens totally on its own, spontaneously. So what's happening? The zinc is going from zinc metal to zinc 2+ ions, right? You've got zinc turning into zinc 2+ by surrendering 2 electrons, right? It gives up electrons. Is that oxidation or reduction? Remember, oil rig, it lost electrons, so it's oxidized, right? So this is your oxidation reaction. Meanwhile, you had H+ ions that were in solution, say from an acid, picking up an electron to form half of an H2 molecule. Right? So spontaneously this is happening, right? This setup is important because this is how we measure standard reduction potential. They always, on the right-hand side, they always use this hydrogen ion producing hydrogen gas with like this little platinum catalyst material. And on the left-hand side, they put different materials. And what they do is they measure the voltage that accompanies this, right? We know that electrons have to be traveling across that little wire along the top. So you put a little meter up there and you measure the voltage. And what's interesting is that we can do this ourselves, right? So I had the TAs who are awesome put this together for us. I'm going to switch to camera real quick. There we are. Okay. So let me move this so you can kind of see it. Okay, we've got a voltmeter here. We're going to read a voltage. And then I've got these stacks of coins. I've got two things. I've got a stack of zinc and steel washers on the right. And on the left, I have a stack of pennies. But the pennies, we've sanded one side of them. What's a penny made out of? Anybody know? Is it pure copper? No. The outside is pure copper. Actually, it's not even pure there. It's mostly copper. And the inside is what? Zinc. So what we've done is we've sanded off one side of these, right? So that the zinc is showing on one side and the copper is showing on the other. And then we stack these things up. Zinc, copper, zinc, copper, zinc, copper. And let's take a look what we find. When I grab this, I'm going to pick this stack up and move it on top of this aluminum foil. Oh gosh, Emily, I'm ruining your experiment.
Does that piece of paper like resemble the salt bridge?
It's exactly what that is. We're going to describe it in just a moment. It's exactly what it is. If I take this, hopefully I didn't ruin it just then. It's tricky. All right, can you see? All right, there's our meter there. This is less than ideal. Let me prop this up. Okay, you can see a voltage there. So I'm going to put one of these leads on the bottom and one of these leads on the top of our stack, and we read hopefully a voltage. It's jumping all over the place, but it's around 3 volts, right? Just by stacking up, I don't know how they've done. They've done like 8 stacks of things. Is this the yellow one? This is yellow, right? Now, if we take an LED, we're gonna have to turn off the lights to see this. if we take this LED and I put the short end on the foil and the other end on top of it, hopefully you can see this. This should, oh, come on, maybe. Oh, see that? We're actually lighting an LED with a tiny homemade battery, right? So let's do one more here. We've got, now on the other stack, that was zinc washers and steel washers that we stacked together. Zinc and steel. Hope I'm not ruining this. I'm going to stack it up. We could measure a voltage on this just like before. Oh gosh, I think I've messed this one up. We'll see if it works. If it's shorting out, it won't work, and I might have just done that. I'm going to try and do the same thing here. Lift up the foil and touch the two ends. Maybe. No, I think I'm shorting. All right, I'm going to skip that one. So, what have we done there? How on earth is that producing enough electricity to light up a tiny LED? It's not great, but it's lighting up. What's happening? For this LED to light up, what does it have to have? It has to have a current running through it, right? So when I connect it to the bottom of the stack and then touch it to the top of the stack, there must be a voltage inside of there that's driving a current through the LED. And a white LED takes like 5 volts, a yellow one takes a couple volts, maybe 2, right? So different voltages. So why is it when we stack these different metals together that we get a voltage? Let's talk about it. It has to do with the different metals have different what's called reduction potentials, meaning how easily they, in this case, pick up electrons, add electrons from an ionic state. And what's interesting is that if you take, say, like iron and copper, and you connect them in beakers like this, if it's iron and copper, the iron will get dissolved, meaning it's oxidized, and the copper will precipitate out from the solution and precipitate onto that rod. But if you take iron and zinc, now it's zinc will get dissolved and iron will get precipitated. So it's not like one metal is always the one that's going to get dissolved. It depends on what the other metal is that it's in contact with, right? Here's how we know. If we wanted to predict which one's getting dissolved and which one's not going to be dissolved, we can predict it. We do it as follows. We use our standard reduction potential. This is just a picture I took from the table in your book. What this is, it's a bunch of different metals all on the left-hand side in their ion state, meaning they're something +3, +2, +1, right? There as an ion that's lost an electron. You're going to add the electron to them to form the regular metal. What it reports is the voltage associated with that. And positive voltage equals spontaneous. And I know that we just got done doing thermodynamics where a negative free energy was spontaneous. I didn't make the rules. I don't know why they chose positive, but a positive voltage is spontaneous, right? And then down here, these ones, because they're negative voltages, those won't be spontaneous. We generally call these things more reactive. So for example, gold ions picking up 3 electrons to form gold metal has a very high positive voltage, meaning it's very favorable and spontaneous. You want that because if you're going to wear a wedding ring, you don't want it to corrode and look gross if it's made of gold. You want it to always look shiny, right? So noble metals, gold, silver, some of these other ones, they have very high reduction potentials, meaning they very much thermodynamically want to be picking up electrons to form their regular metal. Whereas other things, say sodium metal, because this is a negative voltage, you could write the reverse reaction, sodium metal turning into sodium ions plus electrons. That is very spontaneous. And if you've ever taken or seen on YouTube them take a block of sodium and throw it in a lake, it's extremely favorable. It actually like explodes, right? It wants to get rid of its electrons so badly that it's a pretty violent reaction, right? So that these tables are actually pretty useful. Now, how does this table help us answer the question of whether iron and copper, which one gets dissolved and plated versus iron and zinc? Let's do an example. Let's write it out. Let's do iron and zinc. Okay. Let's write out first both equations. We're going to say iron 2+, picking up 2 electrons, forms iron metal. Bring this around so you can hear me. Meanwhile, zinc 2+ can pick up 2 electrons to form zinc metal. We can look up what the voltages are for both of these reactions. For iron, the reaction is right here. Right? Iron 2 plus 2 electrons forms iron. That has a negative 0.44. The V naught equals negative 0.44 volts. Right? Meanwhile, zinc is down here. It is zinc 2 plus 2 electrons gives zinc. That is negative 0.763 volts. What happens is that these are both currently written as reduction potentials, but we know that every redox reaction, and electrochemistry is redox reactions, has to have both an oxidation and a reduction. So what we're going to have to do, since we have two reduction reactions, we're going to have to flip one of them. So instead of picking up electrons, it's losing them. One has to be oxidized. So how do you know which one's oxidized? The one that is less stable, which is the more negative one. The compound with the most negative voltage is oxidized. So that's one that we're going to flip, right? So we're going to take this equation, we're going to get rid of it, and we're going to rewrite it as an oxidation. So it's now going to be zinc metal reacting to form zinc ions plus 2 electrons. The voltage gets flipped. It used to be negative 0.763. It is now going to be positive 0.763 volts. Okay? Now when you add these two equations together, the 2 electrons would cancel on both sides, and we could write a combined reaction, which would look like the following. It would be iron 2 plus ions that are in solution plus zinc metal will react to form zinc 2 plus ions in solution plus iron metal. So in this case, this basically says exactly what the observation is. If you put zinc and iron both in little beakers, you connect them electrically, you'll find that zinc dissolves, it goes from metal to ions, whereas iron precipitates. The iron ions from solution precipitate out onto the piece of iron, right? And the reason for this is because now that you have these two reactions, you can combine their voltages. Positive 0.763 plus negative 0.44 gives us a overall positive voltage of 0.323 volts. And we said positive voltages, that's just the same as having a negative delta G. It's favorable. So this reaction as written is favorable. Are there any questions so far on using these tables? Timothy. Or Thomas, sorry.
Will the one that's most spontaneous travel through the wire or the salt bridge?
Great question. So in order to have, imagine this scenario up here for a minute, right? If we connect these two things together with a little wire, we know that electrons are going to do what? Or we could look at our diagram, right? Electrons, we're going to have zinc giving up its electrons to form zinc 2 plus ions. So over here, I don't know which one's which. This is a different reaction. So this is the one that's dissolving, right? So the one that's dissolving, the electrons are traveling that way. So if electrons travel that way, eventually you're going to build up a charge, right? You're going to have a positive charge, right? You're going to have I drew that backwards, sorry. You're going to have an electric field, right? You have delta positive here, delta negative here, which will eventually cause your species, all your electrons that are coming there will experience their own electric field and it'll stop moving. So if you don't connect these things with a salt bridge, this thing that connects the two beakers over, your corrosion can't occur. What does the salt bridge do? It provides a means where salt ions, something like sodium, can travel in that direction as well. So for every one electron that's traveling that way, you have a salt ion, some sort of sodium cation also traveling that way, so that there's no buildup of an electric field. If an electric field builds up, it would stop. Okay? First a hand here, then here.
So is this solution some kind of salt?
Yeah, you typically, so for example in here, in these stacks of coins, what Emily did for us, she took the pennies, and in between the layers of pennies, she put a piece of filter paper that was dipped in salt water. If you don't do that, this will not light up, you will not create a battery. Inside every battery, you have to have anode and cathode, that's where the oxidation and reduction reactions take place, and then you have to have an electrolyte, which is just something that has salt ions, some sort of charged ion that can move. Because otherwise, if those ions can't move, it will just cancel out, right? It'll build up its own electric field that will resist further electron movement. Griffin?
So in the water electrolysis, sometimes people add in salts to speed up the process. Is this for the same reason, or is it because another?
I better not say. I don't know offhand. I could look into it. I don't know for sure. Brennan?
If the
if the two metals or potentials are far enough apart, is it possible for there to be a noticeable charge buildup before the corrosion stops?
Sure. In fact, if you look at these, because one's precipitating and one is dissolving, very quickly actually, you can look at one of these. Let me pull up the camera real quick. So this was a nice shiny steel washer moments ago. Oh, oops, oh my gosh. Typing camera there. This was a nice shiny steel washer, and now it is, I don't know if you can see that. It's pretty dark. It's got lots of black corrosion. It looks terrible. It's black and corroded, right? Okay. Let's move on. So does this make sense? I could give you any combination. I could say you take a piece of nickel and a piece of silver. You put together one of these, what's called galvanic cells, and you could tell me which one should corrode and which one will be plating onto it, right? Which one will dissolve, which one will have things plating onto it. Question in the back?
So what do you use to connect those things?
Great question. These ones, we literally just push them in contact with one another. But you could do lots of other things. We'll actually talk about an example. If anybody heard of the word sacrificial anode before? If you have a water heater in your house, you have a sacrificial anode. So we'll come back to that. Okay, so you know how to calculate this delta V. When you combine these together, this is now called the delta V naught. We call that the overall cell potential. To calculate this delta V naught right here, all you have to do is add together your reduction and your oxidation half cell reaction potentials. Again, you have to flip one of them because you can't add two reduction potentials together. That's not a redox reaction. You have to flip one of your reduction reaction potentials so that it's an oxidation potential, and then you can add them up. Okay. However, this is completely analogous to delta G naught. Remember, delta G naught, that was the theoretical part of whether a reaction takes place. But there's theory and there's experiment. And electrochemistry is the exact same. In fact, you can go from delta V naught to delta G naught with this equation. If you wanted to calculate delta G naught for a reaction, say this reaction right here, we could calculate delta G naught for that reaction with this equation. The equation says that delta G naught equals negative N. N is the number of electrons transferred, times F, the Faraday constant, times delta V naught. So our delta V naught is 0.323 volts, right? So if we were to calculate this, we'd say that there's 2 electrons involved, negative 2 times 96,500 coulombs per mole, multiplied by 0.323 volts. And if you do a coulomb times a volt, I'm pretty sure that that's a joule. I'm almost positive it is. So this would come out in the units of energy, right? So pretty straightforward. This is why we teach these two things hand in hand, because they're totally analogous. And just like this is the theoretical part, but you need both the theory and experiment, we need to address the experiment part. So how do we do that? Well, what that's basically saying is how will temperature and the concentration of your ions in solution change the outcome, right? Just like the experimental conditions of whatever reaction can change its outcome, the same happens here. So this is what we actually have to work with. The full equation is right here. It has the experimental component right there, and it has the theory component right there. We just calculated theory from our table. That's the one where you take the two, add them together, make sure that the electrons cancel out, and you get the what's called overall cell potential, delta V naught. However, you also need to include the stuff over here. You have R and T, just like from before, gas constant times temperature, divided by N and F, the number of electrons involved in the transfer. That needs to be balanced, by the way. We'll do an example where it's not balanced, where we have to balance it ourselves. And F, Faraday's constant. And then here, you do it natural log of, before it was Q. So what do we have here? This is still Q. Q is still products over reactants. Right? So what we have here, we have a solid. So that just gets a value of 1, meaning we can ignore it. We have a solid, meaning we can ignore it. And now we have 2 ionic species. If you have species that are ions, even though they're in a liquid, we have to account for them. And the way that we do it, we don't use partial pressures, we use concentrations. So we figure out what's the concentration of that ion in the solution, right? And then it's products over reactants. So our product is zinc 2+, our reactant is iron 2+. And if you look down here, it's going to be your product will always be your oxidized species, So the concentration of whatever your oxidized species is divided by the concentration of whatever your reduced species is. All right, we're going to do an example of this. How about this? What if one of your reactions has one electron transfer, but another one has two, right? So let's do this for, what do I have? Silver, right? Silver ions, Ag+, picking up one electron to form silver metal. That has a voltage associated with it. Is this going to be positive or negative? What do we know about silver? Does it want to corrode? It's going to be a very positive number because silver is one of our noble metals. It doesn't want to corrode. Its value is 0.8 volts, positive 0.8 volts. Meanwhile, let's do it with cadmium. Cadmium 2+ has to, adds 2 electrons, that's right, to form cadmium metal. This has a cell potential, a reduction potential of negative 0.403 volts, okay? Therefore, one of these has to be switched. We have to cross it out and rewrite it as an oxidation reaction. Which one is it going to be? Definitely cadmium. How do we know that? It's the more negative one. And remember, in voltages, positive is spontaneous. So this we're going to get rid of. And we're going to rewrite it as cadmium metal reacts to form cadmium ions, 2+, plus 2 electrons. That means that the voltage turns into positive 0.403 volts. Now, we could go ahead and add these two together now. And when we add them together, do our electrons cancel out? They do not. So we have to multiply that top equation by 2. We would say we're going to multiply this whole thing by 2. Therefore, our final reaction will be as follows. 2 silver plus ions plus 2 electrons plus cadmium yields cadmium 2+ plus 2 electrons plus 2 silver ions, plus 2 silver metal, excuse me. The electrons cancel out, right? The only catch here, and this is important, so you want to write this down. This will make people will always make mistakes on this. You do not multiply the voltage here. Do not multiply by 2. Leave alone. When we did free energy, remember with entropy and enthalpy, we multiplied that term by it. We do not do that here. And the easiest way I think I can explain that is, when you think of electrical current, voltage is sort of like, if electrical current is analogous to like the flow of water in a river, right? Instead of flowing electrons, imagine you have flowing water. A voltage drop is like a little waterfall, right? So we're not changing the height of the waterfall when we add more electrons. We're just sending more water off the waterfall. We're not changing the height of it. That's really kind of the best way I know to describe this. So if you have to just write it down to remember it, then do so, but you do not multiply the reduction potential. It stays constant, right? You do multiply the equation when you add it together. Yeah, Griffin?
What it does do, though, I'm wondering is, like, if you had silver and cadmium in the experiment and you're trying to generate this much voltage out of it, it will take more Ag.
Oh, yeah. Yeah. There's still you need 2 moles of Ag plus for every 1 mole of cadmium metal. Yeah, you still consume more. Yeah, exactly. So therefore, we could calculate the overall cell potential, right? The delta V naught is going to now be equal to the V of the oxidation plus V of reduction, right? In that case, it's going to be 0.403 plus 0.8. So that's what, 1.203? So that's 1.203 volts. Okay, we're almost done. That's delta V naught. We'll end after we do this. But we know that the voltage that this voltmeter is going to read, it doesn't just depend on theory. It's the theory and the experiment. So what you read on the voltmeter will be this value. It will be, what are we calling it? Let me make sure I'm right on terminology. We call it just delta V. So delta V, not delta V naught, delta V equals delta V naught, which we just solved for. And now we have to do minus, with delta G, for free energy, we did plus RT. But remember, because of this pesky negative that somebody thought it was a good idea to include, we have to now minus this term. So it's going to be minus RT over NF natural log of the concentration of our oxidized species. Again, it's products over reactants, right? Sorry, that's 2 plus. That's an ion. So it's going to be the concentration of our cadmium 2 plus divided by the concentration of our silver plus. And then there's one last catch before we're done. This needs to be squared. Remember from our reaction quotients, if we go way back up here to reaction quotients, you took, right here, the partial pressure was raised to the coefficient in front of it, right? There was n sub y moles of y, so we got raised to that ny. If you look down here in the equation that we just did, there is 2 in front of our sodium, in front of our silver ions. Therefore, the concentration of our silver ion, that needs to be squared. If there was 3 in front of it, you'd have to raise it to the 3 power. Okay? So if I told you, and we'll probably start with this next time, if I told you the concentration of cadmium ions and silver ions, now you could finally calculate the voltage which would appear on your multimeter. Okay, we'll pick up here next time.